Good afternoon, everybody, and welcome to the Geo-Institute Summer of Live. We are getting kicked off today with Kyle Rollins' first of three live-streamed Cross-USA lectures. My name is Brad Keeler. I'm the director of the Geo-Institute, and thank you for joining us for another Geo-Institute live stream. This one is extra exciting. Back in 2020, when we couldn't finish out the year with our Cross USA lecturer doing live lectures. That year it was Bob Bacchus of GeoSyntech. We decided we would live stream a few, and it was a hit. And we started doing it every year. So this is our fifth year to live stream Cross USA lectures in the summer, and we are thrilled that you are joining us today. If you don't know anything about the Geo-Institute, we're a technical society with about 12,000 members, most of whom are geotechnical engineers and/or geologists, and we are part of the American Society of Civil Engineers. If you like what you see today, and you are going to, Kyle gives some good ones, everybody. Click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Now, a couple of special things today. For all of you out there who pay attention to history and/or your calendar, you will know that today is June 6th, 2024. It is the 80th anniversary of D-Day, when American, Canadian, and British forces invaded the beaches at Normandy and changed the tide of World War II. This morning, we posted an episode of Director's Cut from 2021 with GI past President Jean-Louis Briot, where he talks about a project he did on the cliffs at Pointe du Hoc in France near the beaches, and how it personally affected him. You should go check that out. It's a very emotional story and a wonderful one to remember on this day. Now, GeoPeer has proudly sponsored the Cross USA lecture for 3 years running, and we have a little video message from them. So we have some technical difficulties with the video, and so what we will do is we will kick to a good old-fashioned radio style read. The 23-24 Cross USA Lecture Series is presented by GeoPeer. When it comes to ground improvement, GeoPeer is the industry leader. With GeoPeer, you can design and build with confidence because we empower you to achieve cost-effective, proven, engineered solutions that meet your project pricing and schedule objectives. We work with you to develop a cost-efficient design that allows for higher design-bearing pressures, greater settlement control, and reduced construction schedules. Celebrating 25 years of project excellence, actually that was last year, the 26th now. We specialize in rammed aggregate pier, rigid inclusions, slope reinforcement, and railway subgrade improvement solutions. There is no soil type or structure that GeoPeer cannot handle. For more information, call 800-371-7470, visit geopeer.com, or email info@geopeer.com. Cross USA lecture was started in 2010 by the Geo-Institute. This is our 15th year doing it. We've had a number of illustrious speakers throughout the years. It is selected by a combination of the GI Board of Governors, the Local Involvement Committee, and the Grad Student Leadership Council. So from our Local Involvement Committee today, the chair of that esteemed body is Jay McKelvey, and he's going to tell you a little bit more about the lecture series and introduce Kyle Rollins, our speaker today. Jay, you're up.
Hi, everybody. I'm Jay McKelvey. I'm with Earth Engineering. I'm the chair of the Local Involvement Committee. The Local Involvement Committee, in case you don't know, acts as a bridge between the GI and the individual chapters across the country. We have 10 members that reach out to the individual chapters across the regions. As Brad indicated, the Cross USA lecture falls under one of our tenets. We meet with the Board of Governors, specifically the past president, and also the Student Leadership Council Board. From that, we produce a list of nominees, and that gets whittled down to one person who becomes our Cross USA lecturer. That lecturer will then go and do 5 presentations across the country, 3 of them for membership firms and 2 to student areas. If you're involved with a chapter and you wish to have the Cross USA lecturer come and speak at your meeting, there's an application that's due very soon, so please look after that. After the lecturer does his 5 presentations, and there's a series of 3 YouTube presentations, of which this will be the first one. It's my honor to present Dr. Kyle Rollins, who will present our lecture today. Dr. Rollins received his BS from Brigham Young University, his Ph.D. from Berkeley. After working as a geotechnical consultant, he joined the engineering faculty at BYU. Following his father, who was previously a professor there, he supervised more than 130 graduate students and has published over 190 papers. His research is involved with liquefaction assessment of gravels, lateral resistance of piles and pile groups, passive resistance of bridge abutments, lightweight cellular concrete for retaining structures, and various soil improvement techniques. Professor Rollins was the chair of the Geo-Institute Tech Committee on Soil Improvement and has been recognized by ASCE with the Huber Research Award, the Wellington Prize, and the Brigham Hayward Baker Award, and this year was the recipient of the 2024 Seed Lecture, which can be found on YouTube as well. With that, I would like to present Dr. Rollins, who will present his paper, Lateral Resistance of Piles Behind MSE Walls.
Okay, let's see if we can get on here.
Looks great.
Looking good. All right. Hello, everyone. I'm happy to be able to be with you online, and I appreciate you tuning in, linking in, or however you want to talk about it, to listen to this presentation today. I'm also thankful to GeoPeer for sponsoring this lecture series, and it's been really a great pleasure to participate with everyone. We want to acknowledge our sponsors for this study. This was funded by a federal highway pooled fund arrangement. There's 2 pooled fund studies that were involved here, and these are the 11 states that participated with us. We're grateful for them contributing to make this happen for us. And in addition, we had in-kind contributions from Reinforced Earth Company, SSL Incorporated, who provided the reinforcements, Atlas Tube and Spartan Steel for the pile foundations, and Desert Deep foundations for the pile driving. Without these in-kind donations, we wouldn't have been able to do what we were able to do. They were just tremendous. Appreciate their help. We're going to talk today about piles behind MSE walls. It was pretty typical years ago.
Kyle, before you go on, can you go into presentation mode for everybody?
I thought I was.
It's not full screen. Give it a click and see what happens. We're seeing all the slides on the left.
Oh, weird. Are you seeing full screen now?
We are not.
Not. Let me, should I go? I'm going to stop sharing and go back in here.
And we'll try again, yeah.
Get the right one. What are you seeing now?
Still the slides. I think we're just going to have to deal with this.
Still slides?
Yeah.
Unbelievable. Okay. Try one more thing and see if this will go. Windows. That's what I'm doing. And then when I go to full screen, you're losing it, huh? Okay. Anything different? No.
Nah, we'll just use this view.
All right. Is it changing with animations? So it used to be fairly typical for to have a slope adjacent to the piles supporting a bridge abutment, but now it's more typical to get extra right-of-way space to have a wall in place, MSE wall with reinforcements extending back into the slope to stabilize the wall, and that resists the lateral force that's developed on the piles. Now, in many cases, we see abutment piles near MSE walls. This on the left is a full scale or a full height MSE wall, where the piles are about 3 diameters behind the wall. And on the right's a wall out in Florida, where the piles are 2.5. These are concrete piles. You can see about 2.5 diameters behind the wall face. So there are many applications where this is going to be a concern. In terms of MSE wall geometry, we're going to talk about the height of the wall, H, and the length of the reinforcements, L. And then the spacing behind the wall, S, is going to be the distance from the back of the wall face to the center of the pile here. As loads are applied laterally to the pile, shear planes develop outward on either side as the loads fans out. And we're concerned now about the decrease in lateral resistance as the wall, due to the presence of the wall. And we're concerned about the pile load and how it might increase the force on the reinforcements. So there are different approaches to this problem. One approach is to essentially ignore the soil resistance and treat this kind of like a big flagpole loading. And the consequence of that is that you'll have to increase the cost from the larger pile diameter or have more piles. Another approach to the problem is to say, let's increase the spacing from the wall to eliminate the or reduce some of the interaction between the pile and the wall. Of course, that increases the cost because you'll have a larger bridge span, and bridge cost is really sensitive to the span length.
Okay, Kyle, I got to cut in again. The slides are not going anywhere in our view. We're seeing the same one. We're all still on slide 4.
Really? Okay, let's.
So I think maybe the thing to do, go back into the sharing to the screen you were in, and then there's a present in Teams button at the top of the screen when you go into PowerPoint. So share your PowerPoint screen. Same way that you were doing it before.
Yes.
And then once we get there, we'll try see a present in Teams button right under your name and icon at the top of the screen.
Nope, I'm not. How about I just let's Okay. Okay. This is going to make me browse for something. No, that's not going to work. How about I go to present with the entire screen? Will that work?
Let's give it a shot.
Let's give it a try.
Yeah. Try clicking around a little bit.
Is that working?
We're still only seeing one slide that says approaches to the problem on it.
Okay, that's
all right. Here we go.
all right. Sorry.
Thank you to all the viewers for your patience. Sorry about this today. We're going to get going now.
All right. So we're looking at how the wall would decrease the lateral resistance and how the pile load is going to increase force on the reinforcement. So one approach is to ignore the resistance, and that leads to more piles or larger diameter piles. Another approach is to move the pile further back from the wall face to reduce the interaction with the wall. And that it leads to a larger cost due to the increase in bridge span. And another approach would be to estimate a reduction factor. And the question would be, what should the reduction factor actually be? So that's anyone's guess, because there's has been very little information to clue us in on that. Some of the best testing before we started our work was from Pearson and et al., a study from University of Kansas. They involved a 3-diameter shaft with geogrid reinforcement, as you can see here, and a masonry block wall. The piles were short, so they had the tendency to rotate. But you can see the load versus deflection curve here, that as the spacing between the piles decreases, there's a significant decrease in the lateral resistance that's developed on the pile. All right, so that's going to be largely a bad thing. And if we look at the deflection here from that study, we're going to be talking in our study about 3 inches of pile head deflection. And that would lead, in this case, to nearly 2 inches of deflection of the wall, which probably wouldn't be a good thing in many cases. So the objectives of our study was to measure the effect of pile shape and pile sleeves on lateral resistance. That's kind of a side benefit of what we're doing. Then we're going to try and measure the lateral pile resistance versus displacement curves for piles at different spacings behind the wall. We're using rounds, square, and H piles. We're using 2 types of reinforcement, rib strip and welded wire. We're going to measure the increase in distribution of tensile force in the MSE reinforcements that are induced by the lateral loading. And then our next effort was to try and come up with P multipliers that could account for the reduced pile resistance as a function of spacing and reinforcement. And lastly, we wanted to develop pile design or design techniques to predict the reinforcement force that would be induced by the pile loading. Our research philosophy has been one good test is worth 1,000 expert opinions. Wernher von Braun, designer of the Saturn V rocket, made this quote. That's not because we don't value expert opinions. We do. In fact, we all want to be experts. That's why we're listening to presentations like this and going to conferences so that we can learn the latest things. But what it does point out is we need to have enough full-scale tests so that we can understand how the world really works. That's not always done. You may remember the Space Shuttle Columbia disaster. On launch, a styrofoam block fell off the external fuel tank and impacted the wing. Numerical analyses were performed by NASA engineers, and they said this impact wouldn't be a problem based on their studies. But the Blue Ribbon panel that investigated this later on said, yeah, we think it will be a problem, and we want to do a full-scale test. So when they fired that styrofoam block against the full-scale wing, you can see that it blew a hole in the wing and blew a hole in their numerical modeling. So it's important to have large-scale tests to see how things work. But we have to have healthy skepticism for tests. They're not all of equal value. Einstein is reported to say a theory is something nobody believes except the person who proposed it. He had a lot of experience with theories. An experiment or a test is something that everybody believes, except the person who performed it. Maybe you've had some tests like this yourself, where you're not sure if everything got compacted properly, or the strain gauges were working, or if the data acquisition had problems, or whatever. So let's look for a minute at the effect of pile shape. In this study, since we were using round, square, H piles, and so forth, we wanted to take a look at what effect they are having. There are not very many cases where you can find what's happening at a comparison at a given site. So if we look at lateral loads on round piles, as they're pushed laterally in one direction, you can see that part of the about half of the side is reduced in resistance. You're only in contact with the side of it. And then the passive force on the front is aimed concentrically to the middle. And so you have a lower horizontal force that's acting on the face. If we look at the square pile in contrast, as it's loaded laterally, it maintains contact on the side, and all the passive force is directed laterally against the load. Similar resistance would be provided by this H pile as it moves in the weak axis. So because of these different combinations of normal and shear stresses, we might expect that a square or an H pile would give us greater lateral soil resistance than a round pile. Here you see 3 tests. Here's the H pile in orange, the pipe pile in red, and the square piles are giving us higher resistance. Not a huge amount, but higher for sure. So what we did is use lateral load analysis with using PY curve methods, where we're using nonlinear springs to represent the soil and a finite element model to represent the beam. And we used PY curves. In our case, these were sands, so we used the API models for PY curves. We had to do a little playing around to get the agreement, but in ours, we've compacted this to 95% of the standard Proctor. And to get agreement, we needed a friction angle of 45 degrees and a K value of 250 KSI. Now we're getting pretty good agreement here between the measured and computed round pile. And when we use those same properties to predict the load on the square pile, you can see we're under predicting, and it's even worse with this H pile. So something is wrong. We're getting more resistance than we expect. And so what we did is just multiply this resistance that we get from the round pile to get us a resistance for the square pile. And when we do that with a P multiplier that's greater than 1, in this case 1.2, we get good agreement with the load test on the square pile, and good agreement with the load test on the H pile using a P multiplier of 1.2 here and 1.25 there. So what that's saying is we have a 20 to 25% increase in lateral resistance. Well, you don't want to base too much on one set of tests, so we added more soil and did this test over again. And here, to get agreement, we're seeing the same kind of thing, something like 1.2 to 1.25. So we're thinking then that you could expect maybe a 20% increase in lateral resistance for square H piles relative to a round pile. And that's what we expected based on our initial thought about this. Another type of pile you might sometimes see is a pile with a sleeve. So the schematic of this is shown here. We have a corrugated sleeve, corrugated pipe casing. Let's call it a can. And in elevation view, it's just down through the soil profile, put in place before the soil is compacted back up. You can drop in later on when it's more convenient. You could drive your steel pipe pile down through this, or concrete, whatever. And this is sometimes used to reduce the lateral resistance of the pile when you have an integral bridge abutment, and the load on the pile could cause distress. Then what you could do is fill this up with concrete, and on the annular space between the pile and the surrounding corrugated pile, you can fill it up just with loose soil that you just dump into the ground. And the question becomes, how much lateral resistance do we really have for this kind of a pile? Many designers assume that there's almost nothing, or very little for sure. So here's some piles driven through cans. In this case, the contractor put these in place so that they could facilitate availability of pile driving equipment. This is what we are measuring with the piles inside this corrugated sleeve. And this is what you would expect if there was no restraint at all. Dramatic difference. This is the resistance that is similar for both the sand backfill and gravel infill. And what we're seeing is shear zones that extend out beyond the edge. And so as this pile is loaded laterally, it starts to lock up the soil inside the sleeve, and then it starts to load the whole pile towards the right. But now the corrugated pipe is loading the soil out beyond it. So we took a look at this with a digital image correlation camera. So you can see that with the 12-inch pile, we're seeing a failure wedge going out to maybe 3 to 4 feet. When we have the corrugated pipe that's 2 feet in diameter, now the wedge is extending out 6 to 8 feet. So instead of having very little resistance, what we're seeing is that the resistance is quite substantial. There's one way to look at this is what we did is look at L pile. We're using the EI for the 12-inch pile, and we're only using the diameter or the width of the pile. It's 12.75 inches out to this, say, 1/2 inch. And then beyond that, we're mobilizing the full resistance of the soil acting on that 2-foot corrugated pile. And then in between that, we can have a linear approximation. So this is one case where, assuming that we think we know what's going on, may cause some discrepancies here. So in these cases, having an H pile or a square pile gives us maybe 20-25% higher resistance, and using the sleeve with loose infill is actually giving us substantial resistance that we need to account for, and not zero or very low as Stott thought. Okay, let's get back on track talking about testing with piles behind MSE walls. Our first stab at this was to go to sites where they were building a bridge and do tests with different pile spacings. At this site on US Highway 89, we had one pile that was 3.8 diameters back from the wall face, and another was 7.5 pile diameters from the wall. Now, if I were trying to get 2 tests to line up, I'm not sure I could have done any better here than I did. But we were expecting there to be a reduction in lateral resistance, right? So you could say, well, maybe both of the piles are far enough behind the wall that there isn't any interaction with the pile. Or maybe what we're saying here is that the lateral resistance provided by MSE reinforcements was large enough to eliminate any reduction in resistance provided by the wall itself. So that would suggest that if we're maybe 4 diameters behind the wall, and we have it reinforced with rib strip reinforcements, as in the case here, that we would have adequate capacity. Here's another set of test piles at Pioneer Crossing. These are at 5, 2.9, and 1.6 diameters behind the wall. And now you're seeing that as we go closer, we place the pile closer to the wall, we have a reduction in lateral resistance like we were expecting. This is another wall, a 2-stage wall. So it's held up basically by this welded wire grid on the face. This is 22 feet high, LVH of 1.2. And you can see now that we're seeing a substantial reduction going from 6.3 to 2.7 to 1.3. So placing the pile closer to the wall does create a significant reduction in lateral resistance here. But you know, we're some of the problems of using existing bridge sites is you can't control all the properties and you have to take what you get. So my dream was to have a mechanically stabilized earth abutment like this from that would be similar to a bridge, so we could see what's really going on and we'd have enough time to do it. Construction jobs are very restricted. So with these pooled fund studies, we were able to get enough money that we could build an MSE wall that was 20 feet high, very typical of overpasses in the US, and 100 feet long. And we did 24 tests with round, square, and H piles with spacings behind the wall ranging from 2 diameters, pile diameters, to 5 pile diameters. So this was a great opportunity for us. Typically, the profile for an abutment at a bridge is shown here, where this would be the height, here would be the length of the reinforcement. But we don't have any bridge in place here on our wall. So what we need to do is simulate the pressure produced by the approach fill here with a surcharge loading. So we've done that at the suggestion of Pete Anderson at Reinforced Earth Company. It's a good suggestion. And so as we look down on our wall, we've got one side of the wall with piles here for strip reinforcement, another side from welded wire reinforcement. And we place surcharge behind the piles before a test was taking place. Our piles extended 20 feet below the base of the wall, so they're acting as long piles. If we look at a cross section, here's our surcharge pressure of 600 PSF to represent a surcharge from the approach fill. This is our test pile here. Our reinforcements extend 18 feet into the soil. We're loading this test pile against a reaction beam and reaction piles on the back face. So there's no effect of this reaction pile on the reinforcements themselves. The soil we're looking at is a silty sand with maybe about 15 to 20% gravel in the mixture. Classified as SP SM or SM, and we're compacting to this 95% of the standard Proctor density. So on looking at our tests, we've got first built the wall 15 feet high. We did some tests on the reaction beams that I've shown you already early in the presentation. Then we did 4 tests on this is the strip reinforcement side. Here's the welded wire side. These were round piles at 2, 3, 4, and 5 diameter spacing. And we did a similar thing with the welded wire side on round piles. Then we did another set of tests with the H piles. We're loading on the weak side, which is what our state DOTs suggested that we do. Then we built the wall higher. Now we've got the wall is up to 20 feet high. The LVH for this case is about 0.7. Again, loaded the piles laterally around the round piles. We've got maybe 5 or 6 feet of soil that's recompacted and virgin soil. Then we tested the square piles. So we have a total of 31 tests taking place at this test site. Here you see the installation of the rib strip reinforcements. These are here's the welded wire reinforcements. They're instrumented with strain gauges so we can monitor the force that's developed, tensile force that's developed in these reinforcements as the load is applied to the test piles. And here's a summary of the The students that were helping on this project, some of them look a little more happy about help with the project than others, but they were all great students that made it possible for us to get this job done. Compacting away from the wall, we used roller compactor, and it was easy to get 95% compaction of the standard relative to the standard. We used jumping jack compactors around the piles themselves. Up close to the wall face, within about 3 feet or so, we're compacting with plate compactors. So we typically get a little lower relative compaction, maybe 88 to 94% we're seeing in this case. And that's kind of typical of real performance. That's done so we don't cause the wall to bow out and be distressed. So our typical test setup here has a reaction beam that's loading against these reaction piles. There's 3 of them here. And these are the precast concrete blocks that are serving as a surcharge. As we look closer, we have a strut that goes towards the test pile. And looking down on there, we have a hydraulic jack applying load with a pin connection, so it's a free head pile. This shows the load versus the pile head load versus pile head displacement. For one of the tests, this is the furthest one back was at 5, and we go 4.3, 3.4, and 1.8 spacings. That's reality for you. We can't quite get them exactly 5, 4, 3, and 2. They move around a little bit, but you can see as we're going from 5 diameters and getting closer, we're seeing a reduction in the lateral resistance due to interaction with the wall face. Now, these are all, as you see, maximum loads, maybe 40 to 60 kips in our test at a wall displacement of 3 inches, or a pile head deflection of 3 inches. We had a digital image correlation set up so we could capture the movement of thousands of points on this wall, and they can give you color contours that show us the displacement of the wall on either the face behind the test pile and in various locations around the wall itself. This is very helpful in understanding what's really going on. This shows the maximum wall displacements that we measured with the DIC and string pots. For 1-inch pile deflection, we're seeing a maximum wall displacement of about 0.1 inch. So that's a fairly minor wall deflection. And if we look at 2 standard deviations, we might get 1/4 of an inch. If we accept 3 inches of pile deflection, then for these 12-inch diameter piles, they're all 12-inch diameter piles, the average deflection goes up to about 0.3 inches. And these, again, are for loads of 40 to 60 kips. So even with our full load developed at 3 inches, we're having displacements at the wall face that are generally acceptable. These MSE walls were designed without any consideration of lateral loads from the piles themselves. So this is some of the excess capacity that we have that's controlling the displacements. We've also can look at the displacements of the ground in front of the pile. As you go further away from the pile, the displacements decrease. This plot on the right, we're normalizing by the displacement of the face of the pile. And as we've gone out to 2 pile diameters, we've got to maybe 20% of the displacement of the face. And at 4 diameters, maybe at 10% or less displacement, rather relative to the displacement of the face. So you can see there's a big reduction in the displacement at the wall face. So let's look at the reduction factors, these P multipliers that we need to account for this wall interaction. Once again, we're using PY curve analysis to analyze our performance. And again, PY curves from API sand curves. So what we're going to do is look at the PY curves from a location or pile away from the wall, and we're going to reduce that PY curve away from the wall by a P multiplier we'll call P sub MSE to give us the PY curve near the wall. Okay. Similar kind of things have been done with group interaction and with piles in liquefied soil. So what we did first then is calibrate our model with the pile furthest away. This was be 5.2 diameters in this case. And once we got those parameters, soil properties, friction angle, stiffness, and unit weights and so forth all established, then we held those constant, didn't change any of those. The only thing we changed is the P multiplier in this case, so that we got agreement with the other load tests at closer pile spacings. So here this would be 0.95 for the 4.3 spacing, 0.7 for the 3.4 spacing, and 0.3 for the 1.8 diameter pile diameter spacing. So I was curious, how would this compare with what we had 5 different students, each analyzing their own set of 4 piles and producing their thesis. So these are for the different welded wire and rib strip reinforcements, different pile types. They're back calculating the friction angle they need to get agreement with what was measured. And I think that's pretty remarkable. They're all within about 1 degree of friction angle from each other. So that surprised me, but it worked out that way. So this plot is showing the back calculated P multiplier values on the y-axis versus the normalized distance from the wall. This is again the spacing behind the wall divided by that's from spacing behind the wall to the center of the pile divided by the diameter of the pile. Okay. And this is for welded wire reinforcements, rib strip reinforcements, different L/H types. And if you look at the data, these data show that if the P multiplier, or if the spacing is greater than about 4 pile diameters, the P multiplier is 1. Say no interaction effects. Or maybe it's better to say that the restraint provided by the reinforcements is holding the wall in place well enough so that you don't see any effect of the presence of the wall. Now, if we go closer, we space things closer than 4 diameters, there's a significant reduction in the P multiplier, suggesting that we've got less lateral resistance of the soil adjacent to against the pile. And we can approximate this with a best fit line, pretty simple equation. Now, with this kind of information, a designer can decide if it's better to put the pile closer to the wall, sacrifice some pile resistance, but have a tighter or have a closer, a smaller bridge span, or put the piles further away, get more pile resistance, but have a greater bridge span. Okay, so it gives the engineer some power to make some decisions, knowing what's going on. Next, we're going to look at induced reinforce on the reinforcements. You think about this, this is really a complicated problem. You've got pile soil interaction, you've got soil reinforcement interaction going on. And but we tried to isolate some of the key factors that were taking place here, and this one is pretty obvious. As we increase the applied load on the pile from here 6 kips, 17, 28 to 34, the maximum tensile force is increasing. And instead of taking place, the maximum taking place at the wall face, it's taking place near the pile, the center of the pile loading. Another effect is if we move transversely away from the direction of loading, we're seeing a reduction in the force induced in the reinforcements. This one's closer to the pile. This one's further away at one level below the MSE. You can see that reduction here. And this is at level 3 in the reinforcements in this case. This is closer to the pile, and this is further away. So as you move transverse away from the pile, you get less force in the reinforcements. And some of these have a peak in front of the pile because you're intercepting the reinforcement at a distance further away from the, closer to the wall face. So here's what we think is going on. It's a little schematic of the pile reinforcement interaction. Let's walk through this. As we're loading that abutment pile, this lateral force deflects the pile to the left towards the MSE wall face. And as the soil moves to the left relative to the reinforcement, it induces friction on the reinforcements acting in the direction of the wall. Okay. So what that does is increase the tensile force, applied tensile force in the reinforcement. Okay. And it reaches its peak up here at the pile, if we're directly behind the pile. Now on the other side, as that's loaded lateral, as the pile is loaded laterally, the reinforcement acting in with the wall that's moving out, this reinforcement moves to the left relative to the soil, and it's trying to act as an anchor. Okay? So the friction on the reinforcement acts to the right to try and hold the reinforcement in place behind the wall. Okay? So this produces a decrease in the tensile force going back to 0 at the end of the wall. Okay? So we think that's the mechanism that's allowing us to have our peak force near the wall, near the pile, and lower values at the wall face. So we're looking at this problem again and looking at some of the factors. We know that increases in the load increase the force in the reinforcements. And the transverse distance away decreases the force in the reinforcement. Statistically, we can also find out that if we look at this, the vertical pressure on the reinforcement, including the effect of the surcharge, leads to an effect on greater resistance. And so we're going to try and incorporate these. We tried to have a simple equation. We tried and tried, but we finally had to resort to statistical regression equations. And this looks a little complicated, but it's only a function of 3 variables: the force on the reinforcement, the normalized transverse distance from the wall or from the pile, and the spacing of the pile behind the reinforced earth, the MSE wall. Okay. So once you put that in your spreadsheet, you can let it go and no big problems. This plot shows the log of the measured maximum tensile force versus the log of the predicted tensile force. And most of the data, this is the 1 plus and 1 minus 1 standard deviation. And again, this is for maximum loads of 40 to 60 kips. Okay, so our R-square value for 940 observations is 0.71. We could have done a little better if we had included other things, but it makes the equation even more complicated. Okay. If we go to all the welded wire reinforcements, it's again a function of the applied load on the pile, the vertical effective stress, and the transverse spacing relative to diameter. It seems like the reason this vertical stress becomes important in this equation is that the welded wire develops a lot of its resistance from passive force on the crossbars, transverse bars, and this vertical stress has an impact on that. So once again, I'm showing you these measured versus computed tensile forces in the reinforcements. And again, now with over 1,000 observations, our R-squared value is about 0.72. So you think to yourself, can I live with that? Well, if you're a geotechnical engineer, you probably can live with that. And if not, you may be in the wrong profession. I'm not sure, but a lot of our correlations aren't much better than that. But so we're feeling pretty good about this, especially when we look at really controlled experiments looking at pull-out friction that were conducted by Texas Tech. I think there are over 100. This is showing a friction factor for a series of pull-out resistance tests, and you can see that there's a significant variation, a large variation, particularly near the surface in pull-out friction. This is for rib strip reinforcements here, and this is the variation for welded wire reinforcement. So even if we're doing really consistent densities, trying to do our best, there's a big variation in the pull-out resistance, and that I think affects the pile, the force in the reinforcements near piles as well, because most of the resistance is coming near the surface. If we go deeper in the profile, there's less of an effect of dilation, and this is largely due, in my opinion, to the variation in dilation effects that increase the normal stress at these locations. So maybe some of you have heard this quote from George Box, who said, all models are approximations. Essentially, all models are wrong, but some are useful. So we're hoping that our model, even though we know it's clearly not correct all the time, can give us enough of an understanding of the variation that we'll see in forces that we can make an estimate of the force that will be produced on the reinforcements. I saw this quote. I've given you a bunch of quotes so far, and this is from Abraham Lincoln. I found this on the internet. It says, the trouble with quotes on the internet is that it's difficult to discern whether or not they are genuine. So be careful about the quotes on the internet you see. So let's look at conclusions regarding piles near MSE walls. First off, we know that there's significant reductions in lateral resistance when piles are placed closer than about 4 diameters from the wall. Now this is applicable in our tests all to 12-inch diameter piles with loads from 40 to 60 kips. If you use a larger diameter pile with higher loads, we have enough test results that I haven't had time to show you today that the displacement will be greater, but the P multipliers will be reasonable. If we have piles placed closer than 4 diameters, we can account for the resistance by decreasing the P multiplier, P MSE, with a linear equation for smaller spacing. We know that the maximum reinforcement force occurs near the pile location. It increases with applied load. It increases as the pile is placed closer to the wall, and it decreases with transverse distance from the pile. The statistical regression equations that we've developed can account for about 70% of the variation. Other things like dilation effects and variability of the compaction effort and so forth likely account for the other effects. Hey, Brad, when do we want to stop? Now or?
When you're done, we've got plenty of questions for me to give over to Jay. So whenever you're done, stop sharing. You can keep going if you want. The people are still enthralled. So
Look, I've got a few more slides, and then we'll call it a day with my presentation. One of the things you may have been concerned about is the effect of groups. You can see in this photo, there's a group of piles acting behind the wall. And what effect does that have in contrast to a single pile loading that I've talked about previously? Okay, so we rebuilt our wall, and we had a couple piles. These two are pretty close to the same spacing behind the wall, but this one is a little closer, 1.8. But we decided to put a frame together. We're going to push this steel frame with two 120 kip actuators in the field. Here's the MSE wall. These piles are 5 diameters center to center in the transverse direction. And we have one pile that's 4 diameters behind the wall to give us a control. Here's the lateral load resistance versus deflection curve. This is for the 4 diameter spacing, our control. This red one is the pile in the center. It has a lower resistance than the pile at 3 diameters or 4 diameter spacing. We expected that. And then the piles on the east and west side, the 2 outside piles, are giving us about the same resistance, but substantially lower than the pile in the center of the group. So looking back here, this is giving us the higher resistance, and these 2 on either side are giving lower resistance. We normally expect this one to give us higher resistance than that one, because it's further back from the wall. But we think the reason why it's not is that we're seeing some interaction of the failure wedges between the 4D and the 3D test pile in this case. For the group load, we're putting enough force on that we're getting pull out of a block of soil moving towards the wall face. So what we decided to do to account for this group interaction effects is to multiply the single pile reduction factor, P multiplier, which is given by this simple equation. So that's the single pile resistance. And then we want to account for any group interaction effects of the piles in a group along the abutment with this reduction factor. So when we do that, back calculate these P multipliers, the pile on the outside on the east has a value of 0.36. The pile in the middle is 0.94, and the pile on the right is 0.74. This is due to group interaction effects only. Okay. So the average P multiplier for group effects would be 0.68. Now this looks a little suspect to us. It's really much lower than we'd ever expect. If the P multiplier for this group here was the same as it is on this other side, maybe trying to eliminate the effects of this pile out here, the P multiplier for group interaction would bump up to 0.8 from 0.68. What can we compare this to? There's one other study that the University of Kansas did, and they again, as we were talking previously, this is Bob Parsons and his students at working with Dan Brown and Associates. This is a 3-foot diameter round shaft with a cap at the top, cap at the top. These are 2 diameters behind the block wall. And these are going to be loaded as a group in this direction. So back calculating the group interaction effects from the test results that University of Kansas produced shows a P multiplier for group effects in the middle is 0.9, and on either side, on external sides of the pile group, 0.73, essentially the same on either side. Okay. That leads to an average group multiplier of 0.79. Okay. Now, if we neglect the interaction effects in our test, we'd get something like 0.8. So really pretty good agreement if we neglect those effects. Now, trying to apply these to a real project becomes a little difficult. In our case, we had 0.9 for the group interaction effect in the middle, 0.74 and 0.36 on this side, leading to an average group reduction factor of 0.68. Now, what do you do if you have a group of 5 piles or 7 or however many you might have in a row along the pile or the bridge abutment? Well, one thing you could do is use these values at the external edges. But what do you do for the piles in the middle? Do you interpolate from here to here? Do you use the same value? If you use the same value as the other middle piles, then the P multiplier for the group would be 0.78, even if we use this lower value that we had before. And if we use the same value on either side, 0.74, say, that's similar to what Kansas got, and use this value of 0.94 for these interior piles, that would bump us up to 0.86. So what we really need to know is what to do with these other interior piles to give us a little more information. So we're doing a project with our state DOT here in Utah, where we're going to go to a bridge site and have a deep beam to load 5 piles, trying to give us some additional information here relative to for the group interaction effects. Okay, well, thanks for your patience and hanging with me. I've got listed a bunch of references here that give you information about almost all the things I've talked about. I don't know if there's a way to do this, but I'm happy to send this out to anybody that's participating, or maybe this is recorded too. You'll be able to look at these and pull up any references that might help you out. Okay.
Well, great. Thank you, Kyle, for a great presentation. I'll start off with a couple questions. Why were the H piles placed in the weak direction?
That's a really good question, Jay. It was a decision made by our technical advisory committee from those 11 DOTs. And we just had a slight majority that said we want to place them in the weak direction. And that their thinking was that if we have it on the weak direction, this will be more representative of what they do when they have an integral bridge abutment, where they're trying to reduce the stresses on the pile cap at the pile head. And so that's what we did. You'd get a much higher resistance if you loaded it on the strong axis.
Okay. The loads on the reinforcement that you measured, if you were designing the wall, would you add those loads to the tensile reinforcements that the earth pressures would provide?
Yeah, if you're designing the wall and wanted to be more explicit about it, then you could take those forces and you could have the force produced by the various piles in different locations acting together on a reinforcement and compute the force that it's going to take up. And then, of course, that would, you wouldn't use any more necessarily than the total force that you're going to apply, because it has to be transferred into the reinforcements in some way. Prior to this point, there hasn't been a good way to do that. So these equations that we've developed give an engineer at least some mechanism for doing that calculation. Of course, I've worked with some engineers from HNTB, and they've used some of these results with, I think it's Plaxis, but it may be another numerical model. So you could account for some of those things, but you have to account for, again, pile-soil interaction, MSE reinforcement interaction, and the piles acting against the reinforcements and so forth. It's a complicated problem to handle numerically, but it can be done.
Okay, thank you. Bill Stevens asks, can you correlate the tensile strength of the steel grids to the tensile strength of plastic geogrid?
Yeah, if you compare from our tests with the geogrid reinforcements that were used by the University of Kansas, the P multipliers for the geogrid reinforcements are much lower. The back calculated P values, PY, let's try that. The back calculated P multipliers would be on the order of 0.2 to 0.4 for the test that was done at Kansas. So the increased flexibility of the geosynthetic reinforcement leads to less lateral restraint than what we have for these inextensible metallic reinforcements. So we wouldn't suggest that you use these P multipliers for geosynthetic reinforcements. They're just more flexible. Someone could do the tests and come up with that, but we did all that we could manage out of that wall that we had at the time.
Okay. Thomas Fennessy asks, what is the link to the NCHRP research report? Would that be available?
It hasn't come out as a NCHRP study report, but it's published on the Utah Department of Transportation research page. And in those references, I should have put that there, but if you search my name and lateral loads and MSE walls, you'll find that at UDOT's, Utah Department of Transportation's website, research website. And I'll put that in the list of references as well, so everyone can access what they'd like to have out of what we've done.
Okay. Jared Martinez asks, the experiment appears to be based on static pushovers. Should there be any modifications for the pile soil wall interaction for cyclic loadings?
Yeah, that's a really good question. As part of our second phase of this pooled fund study, we did cyclic loading as well. And cyclic loading is a mixed bag because you get the loading it more rapidly, you get greater lateral resistance. But with repeated cycles of loading, you see a reduction in lateral soil resistance. So in our case, with 15 cycles of loading that we applied, that would be maybe appropriate for earthquake loadings, magnitude 7 or 7.5, something like this. The net effect of those two factors was to cancel it out, to compensate for each other. So we didn't see more than a 15% reduction in lateral resistance. We looked at the combination of increased load rate and relative to number of cycles.
Okay, thank you.
We still see the same kind of effects that you saw. So when you're pushing towards the wall, you see a reduction in resistance, and when you're loading, away from the wall, you don't see any reduction in resistance in that direction.
Mohammed Al-Rawami asks, when you tested piles inside the CMPs, did you evaluate if piles were behaving as a rigid body, rotating as a short pile, or pile depth diameter ratios still within the long plastic elastic pile?
That's a really good question. We didn't have we left these piles open, so they were hollow, just steel pipe. We did not have an inclinometer or a shape array as we've had on some other projects. So I don't know exactly what to tell you there, but in the analysis, we assume that we're putting the full pile length into the model and analyzing what's going on there. If we didn't have some resistance being provided deeper in the profile, we probably wouldn't have got the agreement we did with what I showed you there. So my suspicion is that it's acting more like a long pile than a short pile.
Okay.
We only looked at the can or the sleeve in the model down to 20 feet, which is the length of the corrugated metal pipe. You know, but most of the lateral resistance is taken up in that section.
Okay, Max Dmitry asks, will yellow jackets provide the same substantial lateral resistance as a sleeve pile would? How about the effects on the integral abutment walls if using yellow jackets on the abutment piles?
I'm not clear about what is meant by yellow jackets. This is another kind of pile type, maybe.
Okay. Max, if you could just put that in a comment and we can clarify that. In the interim, if H piles were driven through MSE wall reinforcing strips, would the resistance of the MSE wall be reduced?
If H piles were driven through the
reinforcement. You placed the reinforcement around the piles, or the piles were placed within spaces of it. I think what Max is asking, if you drove H piles through the reinforcement, i.e. if it was a roll of geosynthetics, would the resistance of the wall be reduced?
Yeah. If you're trying to drive through a geosynthetic, I'm sure that driving process would disrupt some of the reinforcing capability of the grid. So ours, where all the soil was built around it. We did do another case where we had a 2-foot. This is in the second phase that I didn't have time for today. But we did a 24-inch diameter pipe pile that was driven between the rib strip reinforcements. And we didn't notice any reduction in the P multipliers are fairly similar for that case in comparison to the 12-inch diameter piles where we compacted around it. So my first take that would be that there might be some effects, but it's probably minimal. In our case, the 24-inch pile cookie cut through the sand at the top and then went into the underlying soil below. We didn't see a big compaction effort by in the driving process. So just cookie cut through.
Okay, that's the last of our questions, Kyle. I'm going to pass it back to Brad for closing.
Okay, thanks for the questions.
great questions today and plenty of them, which is amazing. So fantastic job, Kyle. A great lecture to get us kicked off with our summer live stream series here going. And thanks to Jay for moderating us so well and effortlessly today. I have to commend you, Kyle. We had those technical issues at the beginning. A lot of people can't recover from that. You did an amazing job, and you delivered today. So thank you so much for that. For our viewers, we do thank you for tuning in today, and those who asked questions, a huge thank you, and those who responded to the polls and things like that. That is what makes the live stream experience truly valuable for everybody, is the interactivity. So thanks for being here. If you liked what you saw and you're here at the end, so you probably did, you can click like, subscribe, and get notifications. And yes, we will let you know every time we post something to the YouTube channel. Our next live stream will be in 13 days. It's on June 19th. It's episode 3 of the Keller Sustainability Series with Cabri Lehrman-Schmid, talking about DEI, inclusion, and sustainability. And you don't want to miss that one. You can sign up for that and all of our other upcoming live streams on the Eventbrite page. So thanks again, Kyle and Jay. Great job today. Thanks for doing this. We got 2 more Cross USA live streams coming up. July 25th, September 5th. Sorry, you're going to want to be there for both. You can check those out on our Eventbrite page, and we would love to see you right back here for those on those dates. Matt Roberts was our producer today. Thanks everybody for tuning in, and we will see you again very soon.